This is Gas Law Lecture number 7, Gas Stoichiometry. Obviously, we've learned the rules of stoichiometry, so if we can combine stoichiometry with the gas laws, we can determine something that's easier to measure, like the volume of a gas rather than the mass of a gas. You know from previous work in stoichiometry that the grams of A will go to, or we'll take the grams of A to the moles of A, then convert to the moles of B, and then to the grams of B. But now that we know gases, we can take liters of A to moles of A, or moles of B to liters of B, as long as, and this is a key point, it must be a gas. We cannot do that with solids, liquid, or aqueous solutions. Must be a gas. Okay, so let's take the synthesis of ammonia from its elements. So we know ammonia is NH3, and that is a gas at room temperature. The elements that make it up are hydrogen and nitrogen, both diatomic elements. And if we go through and balance this reaction, we'll get a 2 here and a 3 here. So that's the balanced reaction for the synthesis of ammonia from its elements. Now, we want to know the volume of ammonia produced. If 20 grams of nitrogen reacts with excess hydrogen at 20 degrees Celsius and 735 millimeters of mercury pressure. So we're going to be determining the amount of ammonia, but from a different substance. Anytime we're determining one chemical from another chemical, that's a stoichiometry application. So we've got mass of nitrogen and excess hydrogen. That means we don't have to worry about the hydrogen. There's more than enough of it present. The limiting reactant is clearly 20 grams of nitrogen. So we're going to take 20 grams of nitrogen and predict the amount of ammonia that will be produced. So here we have grams of A. We're going to go to the moles of A, then the moles of B. Then rather than determine the grams of B, we want the liters of B, in this case ammonia. So 20 grams, 1 mole of ammonia, or 1 mole of nitrogen is 28.02 grams. Remember that it's a diatomic, 2 nitrogens. And then our stoichiometry step, which is 2 ammonias for every 1 N2. We solve that, we will have the moles of ammonia. So if I plug that into my calculator, I will get 1.43 moles of ammonia. Just a reminder of what that means. This part has nothing to do with the gas laws. This is if 20 grams of nitrogen are completely reacted, we will get 1.43 moles of ammonia. And as you know, we can multiply that by the molar mass of ammonia, get the grams. But we don't want the grams. We want the volume. So now we're going to go to PV equals nRT. The pressure here is in millimeters of mercury. There's 760 millimeters of mercury per atmosphere. So we can just make a mental note of that. 760 millimeters of mercury equals 1 atmosphere. We must do the calculation in atmospheres. So 735 divided by 760 is going to give me the number of atmospheres. That is 0.967. So we have 0.967 atmospheres. Our temperature is 20 degrees Celsius, but as you know, PV equals nRT, we must use Kelvin. So we're going to have 293.15, we'll put it at 0.2 Kelvin. Our volume is our unknown. Our number of moles is 1.43 moles because we're finding the volume of ammonia, not of nitrogen. Now we can plug in the PV equals nRT. So we're going to say, okay, the volume is equal to the number of moles, 1.43, times R, 0.08206, 206 liter atmospheres per mole Kelvin, times the temperature, which is 293. And that's Kelvin. All divided by the pressure, which is 0.967 atm. Obviously, our atmospheres are going to cancel, liters are going to cancel, Kelvin are going to cancel, I'm sorry, liters aren't going to cancel, moles are going to cancel, and we're going to get liters as the resulting unit. So we plug that into the calculator, and we will get 35.5 liters. So, if we completely react 20 grams of nitrogen with however much hydrogen is necessary, it's in excess, we will get a volume of 35.5 liters at 20 degrees Celsius and 735 millimeters of mercury. That inclusion is gas laws combined with stoichiometry.